All right, so what I've done is I'm going to go through chapter 6 for Alex and do some review problems, kind of go over some tips and tricks that I think will make this easier for you. So I noticed that several people emailed me and said that they couldn't get through certain parts of chapter 6. So I went through and I worked the Alex problems and decided that there were a couple things I didn't like. I'm very good at these reactions and reaction rates and stuff. So if anything kind of hung me up or had me even the slightest bit confused, I went ahead and pulled that from your Alex assignment. So you have like three less topics than you did for chapter 6. I've also extended the due date till this Friday. So those of you that are waiting on something like this to help you get through it, I apologize. I meant to do it earlier. CSU site was down Saturday, and then I was out of town all day yesterday. Uh, but that's what I said. I extended the assignment till Friday. So if you're waiting on this, then go back in there and knock out what problems you can. Okay, so if you still need to do some more assignments for Alex, you can go here to review on the left hand side. Click this little arrow down and then pick out exactly which chapter that you need to work on. So I'm going to click on chapter 6. I'm going to click there and I'm going to click start. Alright, so this is having to do with Le Chatelier's principle about balancing. So I want to show y'all a couple little tricks that I use to kind of keep straight everything that's going on in these reactions. Alright, so let me pull this up. Alright, first I want to look at this reaction that they give me. 2SO2 plus O2 will yield 2 sulfates. Okay, so let me write all this down on my pad. I'm going to just write I'm not going to balance them. I'm just going to write SO plus O2 yields SO3. Okay? For any of these reactions, the first thing you want to know is whether or not this is endothermic or exothermic. So it says the reaction is exothermic. All right, so let's think about what exothermic means. All right, exothermic means to release heat. All right, so one thing that's important for all these, we want to distinguish between heat and temperature. All right. Heat is a form of energy, and temperature, so they're both forms of energy, but heat is specific to the energy involved in the reaction, right? Heat is gained, heat is lost. Temperature is an outside force that we can adjust. We can raise the temperature, lower the temperature, but it affects the reaction in which heat is being transferred. All right? So heat and temperature are two different things in these cases, and you want to make sure that you keep them straight. Okay, heat is in the form of energy. Temperature is going to be denounced by degrees Celsius or Fahrenheit. All right? So we said this process is exothermic. So what I like to do is write down, sorry I can't get my thing to come up, is write down which way the heat is going. So for an exothermic process, heat is given away, so this side will have lower heat, okay? And this side will have higher heat. And we'll use that H for heat. Remember, this is something different than temperature. All right. So now I can look at, this is your main focus right here, right? Heat up on the left side, heat down on the right. And that's because this is an exothermic process. If it was endothermic, it would be heat down, heat up. Okay, it'd be the opposite. but this is exothermic, so let me clear this. Let me clear that. Now let's look back at our problem. Sorry. Reaction is exothermic. And so now it asks us a couple different things to consider. We adjust the temperature, we lower it, and we raise it. How will that affect equilibrium, right? So what I'm going to do is write these temperature patterns. Temperature is lowered. So let me go here, and I'm going to say T is lowered, okay? So the way I keep these straight is, like I said, I've wrote this based on whether or not it's endothermic or exothermic. In this problem, it's exothermic. If the temperature matches, if the temperature arrow, which is down here, right, matches the heat right here, in this case it does not, they're opposite. Let me get rid of these. Okay, if these arrows match, then equilibrium will go to the left. If these arrows are opposite, like they are here, then equilibrium will go to the right. So for here, our equilibrium is going to go to the right. Let me clear that. Clear that. Maybe an eraser. Okay. All right, so I'm going to repeat this one more time. Put your temperature on the left side. Set up your heats for whether or not it's exothermic or endothermic. And I'll do another problem here in just a second. If the temperature matches the heat, then equilibrium will go towards the matching arrows, right? If they're the opposite, it will go away from toward the reactant side. So these are opposite. It's going to favor the SO3 side. Let me go over here and start filling this out. So temperature is lowered. It's favoring the right side, correct? So the O2 pressure will go down, right? Shifts it to the right. Temperature is raised, so I'm going to go back here to my table and I'm going to switch this out. So this will be temperature raised, right? These arrows match, so that means equilibrium goes back to the left. Okay? If those arrows, if temperature and heat arrows match, then equilibrium is going to favor the side that they match on. Alright, so now let me fill out my problem. Temperature is raised, so my equilibrium is to the left. SO3 will go down. And check. Alright, so now let's do another one. Let me do more practice, see if it gives me an endothermic. It does. Alright, so I'm going to go here. Clear this off and write my next equation, which is NO plus H2O. NO plus H2O yields, and I'm not worried about balancing the equation necessarily for these. If it had something to do with pressure, then I would worry about that. Pressure in the sense of that's what they're messing with. They're adjusting the pressure, internal pressure. So O2 is the other one, sorry, plus O2. Okay, so they said this was an endothermic reaction. Remember, the endothermic reaction means it absorbs heat, so the heat is higher on the reactant side. All right, higher on the product side, lower on the reactant side. This is an endothermic process. Notice that these heat arrows are opposite from when it was an exothermic process. Now I just add my temperature arrows. Okay, so for this problem, it says the temperature is raised. So I'm going to go back here and put T up. Alright, so this arrow is opposite that arrow for heat, so the reaction is going to favor the right side. Fill that in to the right. The pressure of O2 will go up because my equilibrium goes to the right, correct? Now it says temperature lowered. Sorry, I have to keep going back and forth between these. Let's cut this. Undo that. Cut. Cut. Heat down. And now T down. So what happens if I lower the temperature? Now the arrows match. That means the equilibrium has to come back towards those arrows. So cut that out. Let's fill this out. Equilibrium to the left. And if equilibrium is to the left, the pressure of H2O, which is on the left, will have to go up. Okay? So it's a little bit simpler way. Just put down your temperature. For this problem, you can just write down the temperature and see if it matches what the heat is doing. Okay, if they both go down, then it favors the reactant side. If they're opposite, then it favors the product side. All right, so that should get you through there. Let me clear this off real quick. Now let's look at our next problem. Next topic. Okay, this is the same type of problem, except for now we're adding in reactants or products, and we're going to see how that affects the balance of equilibrium. So what I like to do for these, and I might have mentioned this in my lecture video, but I want to do it again. So it's essentially, let me put this on that, it's essentially like two tubs which are filled with water but connected at the bottom. Okay, so just imagine these two tubs have a certain amount of water in them, okay, but they're connected here at the bottom. So if I put water into this side, it's going to push through and raise the water level on this side, right? So that's how Le Chatelier's principle is meant to work. Anything we do to a chemical reaction will affect the equilibrium in this way. Okay, so like I said, I try to think about it like these little tubs. Let me put in N2 and 3H2. These are from that problem. N2, 3H2 on this side. Then on the other side, I'm going to put NH3. NH3. Alright, so now I have my little tubs. I can kind of go through the problem and see what would happen to the water level, right? Some N2 is added. Alright, so if I add N2 to this side, it's essentially like putting water in on this side. N2's coming in. It asks me to predict what will happen with some of the other things. Alright, the pressure of H2. Okay, so H2 is on the same side with the N2. If I put in more N2, it's going to use up, because every one N2 uses 3 H2s, right? So when I add N2 to this left side, it's going to decrease the amount of 3H2 that I have. Okay, or H2 that I have. So let's go there and we'll say pressure of H2 will decrease, will go down. NH3, let's go back here. If I'm adding N2 to the left side, then the balance on the right has to go up some, right? My new NH3 level is going to be like right there somewhere, so that's got to go up. Let me put that there. All right, and equilibrium shifts to the right. Just to kind of reiterate that, if I put N2 on the left, it pushes down, pushes through, and shifts equilibrium to the right. All right, so to the right, check. All right, so now they got us with some more. NH3 is removed. So this one's a little harder to draw. Let me see if I can't back it up. Back it up, back it up, back it up, back it up, back it up. All right, so now they're saying that I am removing NH3. So this is just like me taking a pail and pulling out some of this water on the right side. Make sure y'all can still see it. So in that case, it would be essentially the same as if I were to dump water in on this side. All right, so that's how you kind of need to think about it. Let me back that up. So now let me see what the questions ask. The pressure of N2, remember, if it's like I'm dumping stuff over here, then the equilibrium has to shift through to there. It has to try to make up for this NH3 that it's losing. Okay, so, oh, there you go. You see the equilibrium shifts to the right because it's trying to make up for this NH3 that I'm losing here. So, equilibrium to the right, I'll fill that out. And then everything else I just kind of follow. NH2 pressure will go down, right, because I'm losing stuff from my left side. You see the equilibrium's to the right. And the pressure of H2, which is also on the left, will also go down. All right, check. All right, yeah, so just try to think about in terms of like this little setup where I have two pots of water that are connected, and anything I do to one pot of water is going to affect the other pot as well. And you just kind of try to keep up with which side you're adding to, which side you're pulling from, which way the equilibrium arrow, which is this arrow that I have written in the pipe there, right here, which way that's going. And then that'll let you answer all of those questions. All right, so I hope that helps with the equilibrium problems. I think I took off one of the harder equilibrium problems. All right, so next up we have, I'm not worried about that. Activation energy and an energy diagram. Okay, so this is actually not as bad. I think people got hung up in what these words mean. So let's kind of do a review of all of these terms that you're going to need to know from energy diagram. So this energy diagram shows me A plus B will yield C plus D on the reactant side. Now the fact that, let me make sure I can see what I see. The fact that this line here for AB is lower than the one on CD, and you see I have some numbers on my x-axis, on my y-axis over here. That's 200 kilojoules per mole at A plus B. So that's how much heat is tied up in A plus B. And then it's about 250 at C plus D. So that means the heat goes up. That must be an endothermic process. If heat goes up, it's an endothermic process. If heat goes down, it's an exothermic process. Okay? And actually, I can tell exactly what the heat of the reaction is because it's the difference in A plus B and C plus D, which is 50 kilojoules. So let me type that in, 50. Next. Can you determine the activation energy? Okay, yes I can. The activation energy, let me pull up my pad real quick again. The activation energy is the difference. So this is my energy diagram. activation energy will be the difference from here to here. All right. So this we call the EA, or energy of activation. All right. So I trace it from the A plus B line to the top of my heel. Remember, if you watch my lecture, I talk about pushing a stone up a hill. That's the activation energy. All right, so the difference in A plus B and the top of my heel would be 150 kilojoules per mole. So let me, yes, I can, and it's 150. All right. Now, can I determine the activation energy of the reverse reaction? Well, yes, I can. So the activation energy going the other way is the difference between this line and the top of my heel again. So this amount is the activation energy for the reverse reaction. So the difference in 250 and 350 would be 100. Yes, I can. It is 100. Okay. Check. And that's correct. So, these problems are not as bad. I think a lot of people just got hung up in what activation energy means and where do I read it from. So the overall energy of the reaction is the difference in A plus B right here, and the final energy, which will be C plus D on this side. Activation energy, if they ask you about activation energy, that has to do with this heel right here, and they're looking for the top of that heel as being how much energy you need to put in to get the reaction going. It's like I said, you have to push a stone up to the top of the hill. Once you get to the top of the hill, you can just let it go and roll, and it'll carry on to the reaction. But getting to the top of the hill is the most important thing for activation. All right, so let me see what else we got to look at. More practice. I didn't want to do that. I'll try to do one of these real quick. A plus B, heat of reaction is an exothermic process because the heat goes down, right? It's 200 at A plus B, it's 150 at C plus D. So that is 50. I guess technically it'd be negative 50. Let's see if they'll let me put negative. Negative 50 kilojoules. Can I determine the activation energy? Yes, I can. It's A plus B, which is at 200 all the way up to 350. Correct. So that's 150. Can you determine the activation energy reverse? Yes, I can. It's 150 to 350, so that'd be 200. Right, check. Good, next topic. All right, equilibrium constant. This one is definitely a little tougher, okay? So an equilibrium constant just tells you how much products you get for every reactant. So you always do products over reactants. Let me get back to my pad real quick. Clear this. No, don't save. K equals products over reactants. All right. So you always want to think about it in those terms. And you have little brackets here because it's a concentration. This problem is a little simpler. It doesn't do concentrations. It just does the molecules. Okay. But the principle is still the same. So the K for this equation is 3 over 2. So let me write that in. K equals 3 over 2. That means I have 3 products every time I have two reactants, okay? And you have to kind of approach this from both sides because you'll see it's in equilibrium. It's already started reacting. I have a different number of reactants and products, okay? So now I need to count how many products I have, how many reactants I have. I have 1, 2, 3, 4, 5, 6, 7, 8 P's, and then I have 2 R's. Okay? So let's do this. Let's put in 8 products and 2, did I say 2 or 3? Let me look back real quick. 2 reactants. All right. Now I need to multiply each one of these by this constant here. Okay. So for the products, going back to reactants, it's going to be, I have to flip it, right? Because 8 is the product side, but if I'm going in the opposite direction, I want to have reactants over products. Now this, like I said, this can get kind of tricky, so you might need to play around with it a little bit. That would be, I do 2 reactants for every 3, so I have made, let's do 8 divided by 3 over 2, which means I inverse and multiply. 16 over 24. I'm trying to think of an easier way to explain it or to do it without confusing everybody. You know what? I think I'll actually just take this off because I don't know if you're going to see much of equilibrium constants in the way that this is worded. I don't want you to have to do fractions. It can be a little ambiguous. Yeah, I'm just going to take this one off. I may ask you something about equilibrium constants, but I don't think it would be this kind of math because you have to go both ways. I make 3 products for every 2 react. Yeah, I don't like that problem. So I'm gonna take that one off as well. You'll get full credit for this problem. So let me see. How do I go? I guess I gotta do it now though still. So 3 over 2 reactants into products. We said that's what, 9 to 2 ratio? 8 to 2. 8 to 2. I think that puts that at 4. And then that puts that at, I have to have the same number, so that's 1, 2, 3, 4, 5, 8 plus 2, 10. It'd be roughly about 6. Yeah. See, I mean, I did it in my head, but there's not an easy way to explain it. So I'm going to give y'all that one. All right, now writing an equilibrium constant, I fully expect you to be able to do. Let me get this off. So as I said, it's just products over reactants. I'm going to get this out of here. New, clear, okay, and I'm going to write down, actually I'm going to do this straight on the assignment because there's no need to mess around with this extra stuff. Give me just a second, I got to get my keyboard over here. products over reactants. So the products are on the right side. That would be CH3, CH3, OH. Now I got to put these little brackets in. So this just signals that it's a concentration. I wish it had different mole values. So if this were 2 CH3OH, I would actually add a exponent here, 2. If that were 3 CH3OH, that would be a 3. Okay, but since it's 1, I don't have to add anything. Alright, now next I need to put my other product, which is a Cl, and it has a minus right there. Close that in, correct, and then let me do this. Yep, that looks good. Now I need to add my reactants on the bottom, so it'd be CH, nope, 3, Cl, I gotta put those in brackets, and then OH. Now, notice that these are not added together, they're multiplied together. So, don't get confused and put your pluses in there. The pluses only go where the reaction is, not in the equilibrium constant. I need to add a little minus there. And this looks like the expression that I think I need. Alright, so that's just products over reactants. If it has a mole value like 2 or something, you need to turn it into an exponent. I'm sure they have some examples of that in the book, so I'm not going to spend too much time on that. Let's go to the next one. Alright, now this has to do with enthalpy, the change in heat for a reaction. And the principle that this is trying to get across to you is just that the reverse reaction is the exact opposite in heat than the forward reaction. Okay? And mole values are directly proportional to the heat of the initial equation. Okay, so let me make sure y'all can see what I see. Okay, so the initial equation is water plus, or liquid water turns into gas water, and the change in heat is 44 kilojoules. Okay, so now it asks me to predict the heat of other reactions using that equation. Alright, so the first one is 2H2O gas turns into 2H2O liquid. Notice that the gas and liquid are flipped from where they were up top. Okay, I wish I had a highlighting thing. So the 2H2O gas, how do I do this? I'm just going to write it on my pad. Alright, H2O liquid turns into H2O gas. Alright. And then that is, what, 44 kilojoules? Can't see. Yeah, 44 kilojoules. And that is 44 kilojoules, what, per mole, I guess it is. Alright, so now it has a series of other equations, and it wants me to predict the heat. So the first equation they give me is 2H2O gas into 2H2O liquid. Okay? Notice that these are opposite now. So what's that going to do? That's going to turn this into a negative. Since I'm going the opposite way, it's going to turn into a negative, and since I have 2 of them, it'll be 2 times that value, so it'll be negative 88. Put that in, negative 88. Excuse me, negative 88. Negative 88. There it goes. Next up, it is 4 times the value that they gave me up top. So 4 times 44 would be 160 plus 16, 176. 176. All right. And then this one is gas to liquid. It's just the opposite of what is up top, so that'll be negative 44. All right, check. There you go. Okay. So notice that these are all ratioed to the original energy. 44 is 2 times 44 to get 88. 4 times 44 to get 176. You might have some kind of fraction like 2/3 or something, but you just divide it by 3 and multiply by 2. Okay, so I think a lot of y'all got caught up just because it is energy, and we tend to think of energy as being tougher, but these are actually not that bad. They give you an equation, and you just have to determine how that equation is different from the ones that they give you below it. All right, if it's double, then you double. If it's the reverse, then you add a negative. If it's half, you divide by 2, so on and so forth. Okay, let's do the next topic. Interconverting calories and joules. We've done unit conversions, so I'm not going to get hung up there. Matter of fact, I don't even want to do that one just yet. But that's the last one for this chapter. Okay, so this is just converting joules and calories. Remember, 4.184 joules equals 1 calorie, and then 1,000 calories equals 1 kilocalorie. So you ought to be able to do this just like we did the earlier unit conversions and prefix conversions from the first part of the course. All right, so let me change out. All right, so that's it. Like I said, I'm going to give you the problem dealing with the equilibrium constant just because I didn't like the way that was worded. And I mean, I've been doing this stuff a long time, and if anything's kind of tricky to me, I know it's very tricky for you, so I'm going to pull that off of your workload. All right, let me know if you have any other questions. I'm trying to get better at this new video. You see, this is my old setup back here. I'm going to do review videos on this because I like to be able to write, but I'm going to still do the lecture videos on the other. So I'll have another lecture video posted soon, and I'm going to do more review videos going forward to get us ready for the final. So let me know if any of these problems are giving you trouble, and I can add them to the review list. All right, so that's it. I will see y'all next time. Bye.